Hello, and thank you for watching this presentation on a high-resolution crustal velocity field for the Alpine-Himalayan Belt from Sentinel-1 InSAR data. Before I get going, I want to acknowledge that science is a team sport and a huge number of people have contributed at some point to this. In particular, I'd like to acknowledge Jonathan Weiss, Milan, Yu Morishita, Chi-U, Chris Rollins, Yasser Magsudi, Lin Shen and Hua Wang, who've all made fantastic contributions in the last few weeks in particular to this presentation. So the focus is on the Alpine-Himalayan Belt because primarily that's the location where most people die in earthquakes. 3/4 of earthquakes killing more than 10,000 people since 1900 have occurred in this region. And we now know that combining geodetic strain information with seismicity data can lead to improved estimates of seismic hazard. So this is a broad summary of the workflow that takes us from raw Sentinel data to through making interferograms, inverting for line of sight velocities. We can then reference those to GNSS data, invert those for 3D velocity fields and strain rates, and combine that strain and seismicity data to estimate seismic hazard. And I want to take you through that workflow step by step in this presentation. Starting with making interferograms. So we do that automatically for 250 by 250 kilometer frames using the LIXAR package that we've developed in Comet and the University of Leeds. And for details of that approach, you can see presentations at this AGU by Milan, who has a poster, or read the more detailed description in Milan's remote sensing article published earlier this year. In essence, we form interferograms with the 4 closest previous acquisitions, and in some cases some additional pairs to improve the network as we need those. And we've now processed something like 350,000 interferograms using this approach, and these are all available for free to download from the Comet LIXAR portal. Of those, about 223,000 are in the Alpine-Himalayan Belt, which is the focus of this talk. Once you have all of that data, you can do things like this, which is plot the coherence over a very large region. So this shows that there's some variability. In fact, it's a really beautiful data set showing the different surface types. So this is a function of vegetation, for example. So once we have interferograms for all of our different frames, we need to invert those frame by frame for velocity. And we do that as follows. First of all, we create average line of sight velocities using LIXBAS, which is an open source time series code based on a modified NSBAS approach. This was primarily developed by Yu Morishita, and you can read his remote sensing article about that or look for his latest results in his AGU poster, the number of which is there. We use LIXBAS to generate velocities for every frame where we have LIXAR data. So that's about 1,400 different 250 by 250 kilometer frames across the globe, covering a total of something like 90 million square kilometers. We do that in this automatic way, just at 1 kilometer resolution, just for efficiency. And this is what the results look like if we zoom in on the Alpine-Himalayan Belt. What you can see is that there are velocities everywhere, but also these tilts. And so we can remove that by simply locally solving for a tilt for each frame. And that gives us this velocity field, which shows much more spatially homogeneous patterns. The quality of this velocity field is somewhat variable in space, and it depends primarily on the length of the interferometric network that we have for each frame, and that varies from place to place and as seen in this map. So we have very good data in Turkey, parts of Iran and Central Asia, and then also some pretty good data for most of the Tibetan plateau. But it is variable. There are some frames where, for whatever reason, the automatic processing hasn't quite worked as we'd have liked. So here are the ascending velocities again, and you can see a number of features associated with water extraction in Iran, these large areas of very strong subsidence. You can also see some features associated with individual earthquakes at various locations in this. We see some very similar features, particularly in terms of the vertical signals in Iran when we look at the descending passes. So once we have all of that, what we want to do is reference that InSAR data into a common reference frame. And essentially, we can do that in two ways. The standard approach, which has been used by Akbar Hussain, Jonathan Weiss and others, is to tie it directly to the GNSS in the first step by, first of all, compiling high-quality GNSS data, interpolating that GNSS data and then projecting it into the InSAR line of sight, and then solving for the best fit plane or quadratic surface to adjust the InSAR velocities into the GNSS reference frame. And these are the data published by Jonathan Weiss for Anatolia using this approach earlier this year. And you can see very, very beautifully the changing colors associated with the North Anatolian fault in both the ascending and descending data, with the different colors reflecting the different viewing geometries. You can then invert those together to give you east, west, and vertical velocities, which again rather beautifully show the broad scale tectonics of Anatolia. You have to make an assumption when you do this. Typically, we might make an assumption such as assuming the GNSS north-south velocities are correct. However, if you're in a region where there's relatively sparse GNSS data, then this doesn't work well because your interpolated GNSS data are not very accurate. So for Tibet, we've jointly inverted GNSS data and InSAR line of sight velocities using the ValMap approach and solved for both the velocities of the nodes on a mesh of spherical triangles and the reference frame adjustment parameters simultaneously. So this is our mesh covering the Tibetan Plateau, showing our InSAR coverage and our GNSS data. Our GNSS data comes from Wang and Shen 2020. And here's the resultant 3D velocity field. What we're seeing here is the east, north and up components of the 3D velocity calculated on our triangular mesh alongside the second invariant of the strain rate tensor. The east component shows us the features you might expect with a gradual eastward motion of central Tibet and some concentrated gradients in that eastward motion along some of the major faults, including the Alpine-Himalayan fault and the Kunlun fault. The northward motion shows that gradual swinging round of the velocities around the eastern syntaxis. The vertical velocities are quite interesting in that they're showing some long wavelength features that are somewhat reminiscent of the lithospheric scale buckling that has been proposed by Bischoff and Flesch. The fit to the GNSS data is shown in the bottom left, and we do a pretty good job of matching the GNSS data with this velocity field. If we compare the velocity field to one where we've only used GNSS data, you can see the GNSS only velocity field is much smoother, as would be expected, as there's a lot fewer observations. We see that again if I bring up the InSAR and GNSS velocity field. You can see a lot more detail there. There's also vertical velocities, of course, in the combined field. We only use a horizontal GNSS data set in this inversion. We can then look at the fit to the InSAR data, first of all, by looking at the original data here in mosaics of ascending and descending data. These have been locally referenced. So essentially a planar ramp has been removed from each one. And you can see already, even in this representation, you see some nice features associated with some of the geological structures in the region. If we then put that into a reference frame defined by the GNSS for Eurasia, we see these beautiful patterns combining all of that InSAR data to give us these broad scale velocity fields. There are a few mosaicing issues, particularly where data are relatively noisy around here on the Alpine-Himalayan fault, for example, in the ascending data. But in general, this simple mosaicing approach works very well when we've done it via this joint inversion. You can then look at the fit to the InSAR data. What you've got here is the observed InSAR data in ascending and descending, the model velocity field from the joint inversion with GNSS, and the residuals. And in general, solving for the velocities in the InSAR reference frame simultaneously, frame by frame, works really well. The jointly inverted velocity field provides a good fit to both data sets. The RMS residual for the InSAR data is 2.3 millimeters per year, and for GNSS, it's about 1.2 millimeters per year. So these are around the level of the noise we expect to see in each of those individual data sets. Once we've got our line of sight velocities referenced to GNSS, we can do a more direct inversion for both the eastward and vertical velocities, in this case by assuming that the north-south velocities, which only make a relatively small contribution to the InSAR line of sight velocities, we assume that those are correct in the GNSS velocity field. What we get out is these nice maps at the InSAR resolution of both the eastward and the vertical velocities. You can do this, of course, a lot better and with a lot more confidence and accuracy and at a higher resolution if you do local bespoke processing in individual areas. This is a lot more effort, but the results are really nice. I'm going to show you two examples. The first is for the Alpine-Himalayan fault, and this is work done by Lin Shen during her PhD that she's just submitted at the University of Leeds. What you can see here is a really beautiful eastward velocity field for the Alpine-Himalayan, and you can look at the change in rates, for example, of slip along the fault, and the results confirm earlier studies that show actually that this branch down to the south here takes up more of the slip rather than the slip going onto the Karakash fault here. Another beautiful example is from northeast Tibet, and this is work done by Chi Yu at the University of Oxford, who has also just recently submitted her PhD thesis. And again, you can see here on the left the eastward velocities, in the center the vertical, and in the right the strain rates derived from the combination of ascending and descending InSAR from Sentinel-1 processed at a higher resolution along with the GNSS data to tie down the reference frame. And in particular here you see this really sharp strain concentration along the Haiwan fault and the Eastern Kunlun fault. Really beautiful result. So really the bespoke high resolution processing gives us more detail and fewer errors than the automatic processing, but of course it's a huge effort. So the final step is to take these data and to use them alongside seismicity data to estimate size. The combination of using geodetic strain and seismicity data allows you to constrain both earthquake recurrence intervals and maximum magnitudes simultaneously, which you can't do with either data set by itself. So for more details of this approach, I refer you to Chris Rollins's talk he's given as part of the Detect series, or you can look at his latest results in his talk for AGU. So to conclude, automatic processing of Sentinel-1 enables us to produce large-scale velocity fields. Joint inversions of velocities and reference frame adjustments is useful, particularly when GNSS data is sparse. Our full Tibet scale velocity field shows broad-scale deformation of the whole region alongside localized strain around major structures. You get better results through detailed bespoke studies of individual areas, but at a huge cost in terms of time and effort. Further refinement of our results, we hope, will lead to strain rates that can be useful for seismic hazard assessment in the future. Thank you very much.